Hi friends, welcome to the lecture of linear algebra. Today we will start new chapter, that is second unit, which is nothing but elementary canonical forms. In last chapter, that is unit first, we have seen something about linear transformations. First we have seen what is a linear functional. After that we have seen all the concepts related to linear transformation, that is characteristic polynomial, minimal polynomial, invariant subspaces, the conductor of alpha into w, eigenvalues of given linear operator. Now we have to see what is that algebraic multiplicity. Algebraic multiplicity, actually we can find out the algebraic multiplicity of eigenvalues. If suppose we have given one eigenvalue of a given linear operator, then how will you find out the algebraic multiplicity of that corresponding eigenvalue? So algebraic multiplicity of a eigenvalue, that is characteristic value in value, is a number of times it appears as a root of characteristic equation. That is the number of times any, suppose we have to find out algebraic multiplicity of any eigenvalue lambda, then how will you find out its algebraic multiplicity? We have to see how many times this lambda which comes as a root of given characteristic equation. That number is nothing but the algebraic multiplicity of that corresponding lambda. For example, if suppose A is a matrix of order 2 cross 2, as it is a matrix of order 2 cross 2, then it is a square matrix, okay, and lambda square plus 4 lambda plus 4 equal to 0 is its characteristic equation, Now, this lambda square plus 4 lambda plus 4 equal to 4 is actually nothing but lambda plus 2 square equal to 0. Since a plus b square is nothing but a square plus ab, 2ab plus b square. Lambda square plus 2 times 2 into lambda plus 2 square, which is nothing but lambda square plus 4 lambda plus 4. Okay, from this, lambda is nothing but minus 2 comma minus 2. So, the given characteristic equation has only one root, which is a minus 2. Now, how will you find out the algebraic multiplicity of this minus 2? So, algebraic multiplicity of lambda equal to minus 2 is, now we have to see how many times this minus 2 is a root of given characteristic equation, and it is 2 times the root of given characteristic equation, so its algebraic multiplicity is 2. Okay. Now, second example is, let A be a matrix of order 2 cross 2, matrix of order 2 cross 2, that is, it is a square matrix of order 2, and lambda square plus 5 lambda plus 6 equal to 0 is its characteristic equation. Okay. Now we have to find out the roots of that given equation. Plus 3 plus 2 is nothing but plus 5, and plus 3 into plus 2 is nothing but 6. So it is the actually nothing but lambda plus 2 into lambda plus 3 will be equal to 0. So roots are lambda equal to minus 2 comma minus 2. Let lambda will be equal to 1. Now we have to find out the algebraic multiplicity of each eigenvalue minus 1 and minus 3. So algebraic multiplicity of minus 2 is equal to, now we have to see how many times this minus 2 is the root of given characteristic equation, and it is only one times it is the root of given characteristic equation, so its algebraic multiplicity is 1. Okay. Similarly, the algebraic multiplicity of minus 3 is equal to, now minus 3 is again only one time root of a given characteristic equation. So again its algebraic multiplicity is also 1. So in this way we can find out the algebraic multiplicity of given any characteristic value. Okay. Now we have to see what is the geometric multiplicity. Geometric multiplicity. Okay. The geometric multiplicity of an eigenvalue multiplicity of an eigenvalue is defined as the dimension of eigenspace corresponding to eigenvalue lambda. That is the geometric multiplicity of an eigenvalue lambda. Here it is a eigenvalue. Which eigenvalue? It is a lambda. The geometric multiplicity of an eigenvalue lambda is nothing but the dimension of a eigenspace corresponding to that eigenvalue lambda. And what is the eigenspace? Eigenspace is nothing but it is a collection of characteristic vectors. That is eigenvectors. Collection of eigenvectors is nothing but the eigenspace. Okay. Now we have to take the dimension of that eigenspace, and we know that dimension of any space is nothing but number of elements in its basis set, and number of elements in basis set of eigenspace are nothing but the geometric multiplicity of that corresponding given eigenvalue lambda. Okay, in this way we can find out the geometric multiplicity of any eigenvalue. How will we find out? First we have to find out its eigenspace. That is, if suppose we have given one eigenvalue, then we have to find out its all characteristic vectors, and from this we have to construct a eigenspace of that eigenvectors, and after that we have to find out its dimension, and that dimension is nothing but the geometric multiplicity of that eigenvalue. There is one important note: the geometric multiplicity is always less equal than algebraic multiplicity. Okay. Now we will take one example and see how to find out the geometric and algebraic multiplicity of the eigenvalues. So here we have to find out all the eigenvalues of a linear operator which is defined from R2 over R2, R2 over R, such that T of xy is nothing but x plus 2y, comma 3x plus 2y. And also we have to find out its algebraic multiplicity and geometric multiplicity of each eigenvalue. Okay. Algebraic multiplicity is also written as a E dot M and geometric multiplicity as E dot M. Okay. First we have to find out its characteristic values, and then we have to find out its algebraic multiplicity and geometric multiplicity. Given that T is a matching from R2 over R to R2 over R defined by T of xy is nothing but x plus 2y, comma 3x plus 2y. Now to find eigenvalues, first we have to write it's a matrix with respect to some basis. As here there is no basis given. As here basis is not given, then we have to find out it's a matrix with respect to standard basis. First, we have to find the matrix of linear operator T with respect to standard basis. Since basis is not given. If basis is not given, then we find out its matrix with respect to standard basis. Standard basis. Okay. Now, as here R2 over R is given, then its basis contains element 1 0 comma 0 1. Since R2 over R dimension is 2, so this one is the standard order basis. Now we have to find out T of 1 0. T of 1 0 is nothing but T of 1 0 from given linear operator 1 plus 2 into 0 plus 3 plus 2 into 0. Okay, so 1 into 1 plus 2 into 0, comma 3 into 1 plus 2 into 0, which is nothing but 1 comma 3. 1 comma 3. So we can write this as 1 times E1 plus 3 times E2. Okay. So T of 1 comma 0 is nothing but 1 times E1 plus 3 times E2, and T of 0 comma 1 is nothing but T of 0, x equal to 0 and y equal to 1. 0 plus 2 into 1, 2. 3 into 0 plus 2 into 1. Again 2 comma 2, which is nothing but 2 comma 2, and which can be written as 2 into E1 plus 2 into E2. 2 into E1. E1 is 1 comma 0. 2 plus 0. Okay, so the 2 comma 2 can be written as 2 into E1 plus 2 into E2. Now we have to write here. We have find out the images of 1 0 comma 0 1. Now we have to write its matrix. Okay, then the matrix of T with respect to given standard basis is nothing but, let us take T7 as a matrix A, which is nothing but the matrix of linear operator T with respect to standard basis B. As so here we get a 2 cross 2 matrix, and it is nothing but T of E1, and this one is nothing but T of E2 and T of E1. T of E1 is nothing but 1 into E1 plus 3 into E2, and here is E1, here is E2. Okay, 1 into E1 plus 3 into E2. Here is 1, here is 3. Here 2 into E1 plus 2 into E2. So matrix A is nothing but 1 3 2 2. Now we have to find out the eigenvalues of this matrix, and eigenvalues of this matrix are nothing but the eigenvalues of the linear operator T. Okay, and eigenvalues of the matrix is nothing but is given by determinant of xi minus a will be equal to 0. Okay, so first we have to take its characteristic polynomial. Characteristic polynomial of A is given by polynomial of A is given by, instead of characteristic polynomial, let us say characteristic equation. Then we can find out easily its roots. Characteristic equation of A is given by f of s is equal to determinant of a minus lambda I will be equal to 0. Okay. So f of x is nothing but determinant of a minus lambda I is nothing but 1 minus lambda into I1 is 2. Here is 3. 2 minus lambda, which is equal to 0. This is f of x. Okay, which implies 1 minus lambda into 2 minus lambda e minus 3 into 2, which is 6, will be equal to 0. So which is nothing but 1 into 2, 2. 1 into 2 lambda, 1 into minus lambda, minus of lambda, minus lambda into 2, minus of 2 lambda, minus lambda into minus lambda, plus lambda square. Minus 6 will be equal to 0, which implies lambda square. Minus lambda, minus 2 lambda, minus 3 lambda. 2 minus 6 minus 4. Okay, which is equal to 0. Now we have to find two numbers whose sum is minus 3 and whose product is minus 4. So if we take lambda 1 equal to minus 4 and lambda 2 is equal to 1, then product of these two terms will be equal to minus 4 and addition is minus 3. So which is nothing but lambda minus 4 into lambda plus 1 will be equal to 0. So from this, the roots of characteristic equation is are which implies lambda is equal to minus 1 comma 4 are the characteristic value of eigenvalues of P or A. Okay. Now here we get two eigenvalues minus 1 and 4. Now we have to find its, first we have to find its eigenspaces, and the dimension of these its eigenspaces are nothing but its geometric multiplicity. Now first let us check its algebraic multiplicity. Algebraic multiplicity of minus 1 is equal to 1, since it is only one type root of a given equation, characteristic equation. Similarly for 4, which is also 1. Now we have to find the eigenspace corresponding to eigenvalue minus 1. First find out with respect to minus 1. To find the eigenspace corresponding to eigenvalue, let us say as a lambda 1 will be equal to minus 1. For that we have to first find out its all characteristic vectors. Let us suppose that let x be a characteristic or eigen vector of minus 1. Okay, that is corresponding to eigenvalue minus 1. Okay, let it be a characteristic vector corresponding to minus 1. Now, as x is an eigenvector, then by definition of eigenvector, it can be written as a into x will be equal to lambda into x, which is nothing but a minus lambda I into x will be equal to 0. But here a is nothing but 1, 2, 3, 2. 1, 2, 3, 2. Sorry, 1, 2 minus lambda into I, lambda 0, 0 lambda, which is equal to 0. Okay. So which is nothing but 1 minus lambda 2 3 minus 3 2 minus lambda, which is equal to, sorry, here we have to write less also, a minus lambda I. Here is x. Take this x as a x and y, which is equal to 0, 0. Okay. So here x y will be equal to 0. Now here, but here we are finding for lambda equal to -1. So put but lambda is equal to -1, which implies 1 minus of -1, which is +1, 2, 3, 2 minus of -1 plus 2 plus 1, which is 3. 1 plus 1 is 2 of xy is equal to 0, 0, which implies now 2x plus 2y equal to 0, 2y equal to 0, and 3x plus 3y is equal to 0. Therefore, from this we conclude that x plus y is equal to 0. So this one is the equation which is from characteristic vector. Now we have to find its eigen space. Let us denote eigen space as, so its eigen space is given by eigen space is given by its contains all its characteristic vectors, that is eigenvectors. Let us denote it by W of lambda, where lambda is nothing but here -1. We have find out here eigenspace of eigenvalue -1, which contains all eigenvectors xy belonging to R2 such that x plus y will be equal to 0 whenever x comma y belonging to real number. So it is a collection of eigenvectors, and which is nothing but the eigenspace. So which is nothing but xy belonging to R2 such that y is nothing but minus x whenever x is belonging to R, where y is nothing but minus x. So which is actually nothing but x comma minus x belonging to R2 such that, such that x is belonging to 0. Okay. Now this one is the eigenspace corresponding to eigenvalue -1. Now we have to find its dimension, as there is only one vector which belonging to given eigenspace, then its dimension is 1. So dimension of eigenspace with respect to eigenvalue -1 is equal to 1, and we know that dimension of eigenspace corresponding to given eigenvalue is nothing but its geometric multiplicity. So from this we conclude that geometric multiplicity of -1 will be equal to geometric multiplicity of -1 is equal to 1, since dimension of eigenspace is 1. Now it remains to prove that it remains to find out the geometric multiplicity of eigenvalue 4. So now we have to find the eigenspace corresponding to eigenvalue 4. Okay, let x be its characteristic vector. As x be its characteristic vector, then by definition of characteristic vector, ax is nothing but lambda into x, which is nothing but a minus lambda I into f will be equal to 0. But a minus lambda I is nothing but 1 minus lambda into 2 3 2 minus lambda x is nothing but which is equal to 0 0. Now which is nothing but here lambda is equal to 4. As lambda equal to 4, 1 minus 4 minus 3 2 3 2 minus 4 minus 2 of xy will be equal to 0 comma 0 0. Okay, now which is nothing but minus 3x plus 2y equal to 0, which implies minus 3x plus 2y equal to 0 and 3x minus 2y equal to 0. Now we have to find its eigen space. Then its eigen space is given by that is eigenspace corresponding to eigenvalue 4, which is equal to, it contains all eigenvectors belonging to R2 such that minus of 3x plus 2y equal to 0 and 3x minus 2y equal to 0 whenever x comma y belonging to real numbers. So which is nothing but x y belonging to R2 such that 3x is equal to 2y whenever x comma y belonging to real numbers. Okay? Minus 3x plus 2y will be equal to 0, which implies 2y equal to 3x, and from this also 2y equal to 3x. Okay? Now, which is equal to x comma y belonging to R2 such that y is equal to 3 by 2 yes whenever x is belonging to R. So which is nothing but x comma 3 by 2 yes belonging to R such that x belonging to R. So this one is the eigenspace corresponding to eigenvalue 4. Again, there is only one vector belonging to this eigenspace, that is linearly independent eigen. There is only one linearly independent eigenvector belonging to this space. Then its dimension is again 1, which implies dimension of eigenspace corresponding to eigenvalue 4 is equal to 1. Again, we know that dimension of eigenspace corresponding to eigenvalue 4 is nothing but the algebraic multiplicity of eigenvalue 4, which implies geometric multiplicity of eigenvalue 4 is equal to 1. So here we have find out the algebraic multiplicity, geometric multiplicity, algebraic multiplicity and geometric multiplicity of both the eigenvalues minus 1 and 4. Okay. So in this way we can find out eigenvalue. First we have to find out eigenvalues of given linear operator, then find out its algebraic multiplicity, and after that we have to find out its geometric multiplicity. Okay. Now these concepts, algebraic multiplicity and geometric multiplicity, are actually used to check whether the given matrix is a diagonal matrix or not. And we'll see now how to find out whether the given matrix is diagonalizable or not. Okay. First, diagonalizable operator. Okay. Diagonalizable operator. Okay. Let T be a linear operator on finite dimensional vector space V. Vector space V. Then T is said to be diagonalizable. If there is a basis B for V such that each vector of this basis B is a characteristic vector. Okay. So what is a diagonalizable operator? If suppose we have given one linear operator T which is defined on a finite dimensional vector space V, then this linear operator T is said to be diagonalizable if there is a basis curly V for vector space V such that each vector of this basis is a characteristic vector. If each vector of this basis is a characteristic vector, then the corresponding linear operator is said to be a diagonalizable operator. There is one another definition for this, or let T be a linear operator on finite dimensional vector space V over the field F, or it is a finite dimensional vector space over V. Then T is said to be diagonalizable diagonalizable if there exists a basis curly V for V such that the matrix of linear operator T with respect to basis B is a diagonal matrix. Either we have to check this or this one. In this, we have to see any linear operator which is defined on a finite dimensional vector space V is said to be a diagonalizable if there exists a basis curly V for V such that the matrix of linear operator T with respect to that basis V is a diagonal matrix. Then we say that the given linear operator is a diagonalizable operator. That is, if the matrix is diagonalizable, then the linear operator is diagonalizable. So either we have to check from this definition or from this definition. We have easy to see from second one. Since here if matrix is diagonalizable, then the linear operator is also diagonalizable. Now, whether these two definitions are equivalent, that is, if suppose given linear operator is a diagonalizable operator, whether its corresponding linear matrix with respect to order basis B is a diagonal matrix or not. Let us check. Okay, let T be a diagonalizable operator. T be a diagonalizable operator. As T is a diagonalizable operator, then from first definition, any operator is said to be diagonalizable if there is a basis curly V for V such that each vector of V is a characteristic vector, which implies there is a basis curly V for V such that each vector of V is a characteristic vector. As each vector is a characteristic vector, then from definition of characteristic vector, that is, let us take this V as, let T be a diagonalizable operator on n dimensional vector space. Let us take here dimension, since we have to check whether its corresponding matrix is diagonal, and for that we require dimension. Let T be a linear operator, or sorry, let T be a diagonalizable operator Generalizable operator on n-dimensional vector space V, which implies there is a basis curly B, that is curly B equal to alpha 1, alpha 2 up to so on alpha n is for V such that each vector is a characteristic vector. As each vector is a characteristic vector, then from definition of characteristic vector, A of alpha I is P of alpha I or A into alpha I will be equal to Ci of alpha. Okay? For all I am in from 1 to n. Now, P of alpha I will be equal to Ci of alpha I whenever I is running from 1 to n. Let us check for P of alpha 1 is equal to C1 alpha 1. This can be written as C1 alpha 1 plus 0 into alpha 2 plus up to so on 0 into alpha n. P of alpha 2 is equal to 0 into alpha 1, sorry, C2 alpha 2, which is equal to 0 into alpha 1 plus C2 into alpha 2 plus up to so on 0 into alpha n, and so on. P of alpha n is equal to Cn of alpha n is equal to 0 into alpha 1 plus 0 into alpha 2 plus up to so on Cn into alpha n. So these are the images of these n basis element. Now we have to find out the the matrix of this linear operator P with respect to this order basis alpha 1 to alpha n. Then its matrix is given by then where these C1, C2 up to Cn are maybe distinct or equal. Okay, where C1, C2 up to so on Cn may be equal or distinct. May be equal or distinct. Okay. Now the matrix representation of linear operator P is given by matrix representation of P is given by, let us check this matrix as A. That is, A is nothing but matrix of linear operator P with respect to order basis B, and which is nothing but n cross n matrix. Okay, here is nothing but P of alpha 1, P of alpha 2 up to 1 P of alpha 1 alpha n. P of alpha 1 is nothing but C1 alpha 1, that is C1 alpha 1 plus 0 into alpha 2 plus up to 1 0 into alpha n. And these are the C1 into up to so on. Alpha 1 alpha 2 up to so on alpha n, and these are nothing but T of alpha 1 T of alpha 2 up to so on T of alpha n. Okay, so here is C1 and all the remaining coefficients are 0. Here is 0, C2, 0, so on. Here is also 0, 0, 0, 0. C1, C2. Now, so here the matrix of T with respect to B is a diagonal matrix by the definition of diagonal matrix. The matrix is said to be diagonal matrix if Aij equal to 0 whenever I is not equal to 0, and here Aij will be equal to 0 whenever I is not equal to j. So this one is a diagonal matrix. As it is a diagonal matrix, then the corresponding linear operator is said to be a diagonalizable operator. Actually, we have seen here if it is a diagonalizable operator, then its matrix corresponding to its ordered basis will be a diagonal matrix. So both the definitions are equivalent. That is, either we can find it is a diagonalizable operator, or we can find out that it's a matrix is diagonalizable. Then we can also say that this given operator T is a diagonalizable. That is, if we find out the matrix of linear operator T with respect to order basis is a diagonal matrix, then we can easily say that given linear operator is a diagonalizable operator. Okay. Thank you for watching the lecture.